So welcome, and we're going to look at renewable energies in a little bit more detail now. In today's lesson, we're going to be looking at and doing calculations with wind energy, hydroelectric, and solar. So what I'll do is I'll outline these three processes individually and then give you the opportunity to try some exercises. So firstly, how does wind energy work? Well, wind energy happens because of something called a convection current. And a convection current is a natural process which uses energy from the sun. So if you imagine these are rays of infrared heating the land, right? So that basically this landfill area becomes warmer. Because of this area becoming warmer, the air above it becomes warmer as well as a consequence. Now, hot air becomes less dense. It expands as the particles have more internal energy. And because it expands, it rises because it's lighter. Now, this sets up a current because as this expands and rises, cold area from colder parts of the geography come in to take the place of that hot air that's rising. Now, in this picture, you have water nearby. So this is the coast, and the water is cooler because the specific heat capacity is much higher. So as you remember from topic 3, water takes much longer to warm up. So the sun is heating up the land, which is getting hotter than the water. The hot air rises and cold air replaces it. So this is quite nice because if you're standing on the beach here, you'll feel a nice breeze. And that's basically an example of a convection current. And this happens locally, like in breezes, small breeze, as you stand on as a short breeze, as you stand on the beach. But this is basically how weather currents work globally, right? Areas of hot air on the planet move, which encourage cold areas to move as well. So here we have convection currents. And these basically demonstrate that you're getting energy from the sun, which is becoming kinetic energy of the wind. And now, because we're very clever as a species, we take that kinetic energy from the wind and we put it to good use. Because you remember when we were talking about how to generate electricity, we said we needed two things. We needed kinetic energy and we needed something to move, and we needed a generator, right? And that's what we've got. We've got the kinetic energy of the air, the wind, turning these blades, right? So that's the first main part of the wind turbine, the blades. And then in the shaft, in the central section, what we have is a gearbox and, more importantly, a generator. And it's the generator here which creates, no, not an appropriate physics term, generates the electricity. And this is a great video to watch later, which I've posted on Classroom. Now, how do we work things out? How do we actually predict how much energy we can get out of a wind turbine? Well, this is the relationship, and I'll go over it. Power, P, equals a half area times rho, density, times the velocity of the wind cubed. And here we have it outlined. Power in watts, I'll say it again, watts, times a half area, meters squared, times density, kilograms per meters cubed, and velocity, which is meters per second, but cubed. Don't forget that cubed. It's important in these questions to maintain the correct units. So you may be changing centimeters into meters, meters cubed, etc. Perhaps not so much with wind power, but definitely with solar power later. This equation can be derived. I wouldn't worry about it right now. What I want you to do today is practice the use of the relationship. but we'll come back to this at a later time. Now, it is very important that you know what the energy transfers are. So we started off with energy, radiated energy from the sun, which becomes kinetic energy of the wind, which then is transferred to kinetic energy of the wind turbine blades, which then via the electrical generator becomes electrical energy. It's quite straightforward. And it's also really good to know what the advantages and disadvantages of wind power are. I mean, obviously, there are some massive advantages. No greenhouse gas emissions, which is great. It's renewable and it's free. I mean, you'd have thought, could you possibly get better than that? But not only is there no pollution, it can be actually quite versatile. So if you need a small generator for an isolated location, like a research base or a farmhouse, a lighthouse, etc., then you can just get a small generator. You don't need to depend on the grid at all. So they definitely have huge advantages. But as usual, nothing in life is free. What are your disadvantages? Well, they are expensive to make. So initially, you do need a lot of capital. This is the important one in terms of physics. Low energy density. That means you need a lot of wind turbines to compensate for, say, in a power station, a fossil fuel or a nuclear power station. Wind speed is unreliable. It's not always windy. It can be noisy. They can be quite far from where you need them, right? So it's difficult to build them close to where the electricity is going to be used. So there'll be associated costs with transporting that electricity. And then basically some people find them ugly, which there you go. Can't please everyone. All right, so that's a measure of the advantages and disadvantages. Now, you can either do the questions now based on wind turbines. That might be a good idea if you haven't got a lot of time to spend in one go for physics. You could just do wind turbines now and then carry on with the rest later. Or you could do all the theory now, just get me out the way, and then just start doing the practice. It's up to you, as long as you do some of each. With the wind turbine questions, I only want you to choose 3. You don't have to do all of them. They get harder as you go. So if you want a challenge, do the last 3. If you just want some basic level 4, 5 stuff, then do the first 3. Second type of renewable energy is hydroelectric systems. Now, hydroelectric systems, there's 2 types. You've got this first one, which involves basically a big reservoir, a dam, right? Basically making that reservoir happen. And then you usually have the power station at the bottom. And I'll explain how that works in a minute. And then the second type is moon derived, which is a tidal barrage. So these obviously don't have the height, but they are much wider in size to generate electricity. And the basic idea behind hydroelectric energy systems is that of potential energy, right? You need water high up, right, at a height, storing all that potential energy. And then when you need it, what you do is, let's have a look first at the basic structure of one of these sun-driven ones, right? You have a river. If I go up to this picture up here and show you, reservoirs are built, or dams are built in rivers, right? So normally you would normally have the river flowing down this riverbed here. So what you do is you build your dam, and that stops the flow of the river and makes it build up this reservoir here. Now, there are many cases of people actually living in this area and having to vacate their homes, losing their homes, so they could make this reservoir happen. Also nature reserves, forest, etc. So basically what you're doing is flooding entire areas. flooding entire areas. And then once you've got that water up there, you've got your dam and you've got your water at a high height. And then lower down, so on the other side of the dam, you have your powerhouse. And the powerhouse contains turbines and generators. But hang on, what do you need to make electricity? Kinetic energy and a generator. So one source, I meant to say, a source of kinetic energy and a generator. So there you go. So here's our basic structure then. Water at a height, and then there's some access, right, between the water and the powerhouse, which goes downhill, right? So what happens? It's time, we need a bunch of electricity to be generated. We release the water, so we open up this gate, right? The water flows through, and as it flows through, it turns the turbine and it makes the generator work. It makes electricity, okay? So why is it called sun-driven? So that's basically how it works. But now, why is it called sun-driven? Basically, it's how does the water get up here in the first place? Well, that's rain, isn't it? So rivers function because of rain. And how does the rain get up there? Well, due to evaporation, right? So basically, the sun gives the water potential energy through evaporation. And then basically, as the rain falls, it accumulates in the reservoir and it becomes potential energy in the water. Oops, that was a bit of a mess. I'm going to tidy this up. Okay, and sometimes what makes this system quite flexible is that sometimes when you don't really, well, you've got extra energy, right? So you're generating more electricity than you need. You can use some of that extra electricity to pump the water back. So what you do is you take the water from down here and you put it back here again, right? So that you've got an extra reserve of potential energy. Now, this type of method is called a pumped storage scheme, which is a special kind of hydroelectric dam. Okay, so that explains how hydroelectric dams work to generate electricity, right? And why they're called sun-driven. And also just a little bit of information on pumped storage reservoirs. There's another video you might want to watch. It's also on Classroom. I suggest you do that now. Now, moon-driven or tidal barrage systems don't come up so often in the exam, but I'll just outline them. These use the tides, the way that as every 6 hours, the movement of water either towards the shore or away from the shore. So we have a nice little picture up here. Okay, so what you get is water coming in slowly, and the height, basically the height of this water starts to go up as the water comes in, or the tide moves out and the water moves the other way. And what you have here is a large barrier which allows the water to go through it, but underneath there are loads of little turbines. And if we look in the bottom picture here, the turbines, as the tide comes in, the water comes in here and it spins the turbines. And what do we get when we spin a turbine? We get a generator producing electricity, right? And then the tide comes out and it moves this way, and that turns the turbines again. Now, some tidal barrages allow for the slow movement of water as the tide comes in, and others actually work with the tides and the waves moving backwards and forwards. But anyway, we don't need a lot of detail as long as you understand the basic premise. Movement of water moves turbines, which turns a generator. And there's another cool video to watch, which I suggest you have a look at now. So here's our energy flow diagram. Here we have either solar energy, right, becoming gravitational potential energy of the water, right? So that's your energy transfer initially. The energy from the sun evaporates the water, giving it gravitational potential energy. Or you have the gravitational potential energy of the Earth and Moon and the Sun arrangement. Now, that's a bit of a weird one. I wouldn't worry about it too much. Just remember that it's initially gravitational, and that's what's producing the tides, and the tides give the gravitational energy to the water. So it's one of those two. Then that gravitational potential energy becomes kinetic energy of the water as it flows. And then from the kinetic energy of the water, it turns the turbines and the coils, and that gives you electrical energy. And in the case of a pumped storage scheme, then what you do is you use some of that electrical energy to put the water back up again to give it gravitational energy. And this is our Sankey diagram for a hydroelectric power station, where we always remember to include energy losses, right? So our first energy loss would be as the energy from the sunlight or the tide gives the water potential energy, some of that water evaporates again. So you do have some water loss, and therefore you have some energy loss. And then when you are turning the turbines, there's friction, always friction, and then you get electricity, and there's always friction in the generator, etc., or heat losses. So that would generate your friction, which causes heat losses. But we do actually have quite a large amount of power out or energy out compared to the stuff we were looking at non-renewable sources, which was always a very small percentage. These can be quite large. In fact, the efficiency of a hydroelectric power plant can be up to 90%. It's a win-win, really, isn't it? Now, how do we do the maths? The maths is fairly straightforward because we're using the relationship for potential energy we've used in the past. You have a mass, which is at a height, and as it falls, you get a conversion of potential energy to electrical energy, right? So the average theoretical potential energy output during time t would be delta EP over delta T. So we're just looking at a mass of water falling. Now, there are two ways to do questions. Actually, what I meant to say was there's two types of questions, basically. The first one is where you have a height of water, like this. There's your height of water. And you're just basically asked to work out what the potential energy would be, and that would be simply the mass of all of this water times G, oops, I'm not doing a very good job of this, times the entire height, right? So it's all of this water here, okay? So it would simply be mgh, and that's how much potential energy you have stored up there. The other type of question is a little bit more complicated. It's when you've got a store of water at a big height like this, and then what you do is, what you have is your power station is much lower there. Now, this is a little trickier, but you just use what you know about potential energy and objects being at a certain height. If you get a question like this one, basically you treat this as an object that's at a height h, but I'm going to change this. You would ignore this height, and you would use the height from the center of this mass down to where your power station is. So this is the real height that you would use, which is basically what you would do if you had a ball at a certain height, right? You would use the center of that object to gauge your height. So here it would be the middle of the water mass, and that would be your h there. Okay, so be careful with those two types of questions. And then thirdly, remember that mass can be found from density times volume. Most of the time you're given a value for density and volume instead. Now, what's important about this is that you check that your density values, that your units corresponds. So density is kilograms per meters cubed times volume, which is obviously meters cubed. So if for whatever reason, which is unlikely, but it could happen, you're given one of those in centimeters cubed, remember to convert it. And it's important to know what the advantages and disadvantages are. So again, bingo, renewable, no greenhouse gases. That's basically a win-win. They're very efficient and they're free. So these are basically our 4 important ones. You don't really need more than that. In fact, I'm not even going to read the rest because these are so massive. I think we should just stick to those. But why are they disadvantaged? What are the disadvantages? Sorry. Well, basically, you do unsettle and completely devastate the local environment where the reservoir is. You might have to flood large areas. So not only do you affect the natural habitat of the many plants and animals, you've got newly built dams, right, which may have to flood villages, towns, and farmlands. What's another disadvantage is you can't just put one anywhere. You've got to have a certain geography and guarantee a certain amount of water or rain is going to fall. Not only that, these things are really, really expensive initially. So you've got to have a mass investment to start with. And then I think basically those 4 are enough. You can read some of the others. And I'll post an interesting video on some of these disadvantages in Classroom. Now, if you're sick of listening to me and just want to do some questions, do that now, or you can listen to the whole lecture. And now, lastly, we're going to look at solar energy systems. Now, solar energy is pretty much at the root of all these types of energy, but we can use energy sources directly from the sun. When we speak of solar power, then we're talking about energy that's directly coming from the sun's rays. And there's literally 2 ways that we can use sun directly. The first way is to use solar energy for heating, right? So we've got heating. Can't really see that. Heating. Using solar heaters. So what we're doing is we're sticking to the infrared aspect of that energy, infrared, and we're using that infrared to increase the temperature of water. And the second way that we're using them is for photovoltaic cells. What we're doing there is we're using the photoelectric effect to generate electricity, to free up those electrons in a photocell to generate electricity. So they're 2 very, very distinct ways. And once again, I've posted some videos that you can look at, which will go into a little bit more detail on both of these. The flowchart is really easy because what you're doing is you're getting, for a photovoltaic cell, you're getting solar energy, literally just becoming electrical energy. And solar heaters are a little bit more complex, but your infrared radiation is heating up water in pipes. Now, the pipes are painted black because black is very good at absorbing heat. And you have a system, a pumping system, which basically takes that hot water into an isolated tank, which basically allows that heat to be used in the home, etc., and then it's pumped back in. And your energy transfer there is just solar energy becoming internal energy of the water. So here we have a heat transfer from radiated to internal. It's important to use that word because what we're doing is we're increasing the temperature of the water. So what are the advantages? Oh, once again, they're renewable, free, pollution-free, low maintenance cost. They do actually last quite a long time. So it's a win-win, basically. Why aren't we using these more? I have no idea. Well, I do have, but mainly for political reasons. But anyway, it's all wins, renewable, free, and pollution-free. Variation of output with time. Now, they do have the disadvantage is in that solar energy is not available 24 hours a day. They can be very expensive to construct initially. Okay, in addition, there are some pollution issues with decommissioning solar power stations or solar paneling. Obviously not as severe as the greenhouse effect, but there are some disposal issues there. And low energy density. This is a very important one for physics. You need huge areas for photovoltaic power stations. Now, how do we answer questions? There isn't a relationship as such for solar power. What you do need to take into consideration is the amount of power that you're getting from the sun. So power comes from the sun, and in designing solar panel systems, what you need to consider is the amount of energy that falls on 1 square meter. Now, you guys should know that, I'm going to write 1 square meter, that this is actually called intensity, right? Intensity is the amount of power per square meter. So it's power divided by area. Now, you need to know, in order to design a solar panel system, you need to know what the intensity of energy arriving on the Earth is. We will cover this in a lot of detail in the next lesson. For now, you'll be given this value. And once you know that, once you know how much energy per square meter is arriving, you can work out how much energy you're going to get out. Okay, because you've got a conversion from solar to, it's going to take me ages to write this, electrical, right? Now, if you have 100% efficiency, then basically all that energy that you get per square meter will become electrical. So let's say, for example, you have 100 joules per square meter, M minus 2, write that in there. Okay, it's 100% efficient. So basically, if you have a solar panel of 1 square meter, you will get 100 joules out, right? If you build a bigger solar panel, so it's 2 square meters, then you're going to get twice as much, right? You're going to get 200 joules. So that's easy. How much energy do I need? And I can now go backwards and design the size of my panel, right? Unfortunately, life is not that easy. What you have is efficiency. So you may need to adjust times 100. Now, most questions look like this. I need 100 joules. My solar panel is 50% efficient. What area do I need? Well, in this case, if you've got 100 joules out, if it's 50% efficient, you're going to need 200 joules to come in, right? 200 joules. And if the amount of sun that's coming in is 100 joules per square meter, you can see that you would need 2 of these 1 meter panels to generate 200. Does that make sense? Okay, so you work backwards. Work out your energy in using your efficiency and what you're getting out. And once you know that, use your intensity value to work out the area of the panel. Now, solar heaters work in pretty much the same way. You would get your energy in, but this time what you're doing is you're heating up water. So you would then use Q equals MC delta T. All right, so how much energy you're getting. Again, you could have energy in, it might be an easy question. You could have power per second. So the question will be about time, right? Or you might have intensity, right? Well, they want you to design an amount of a size of paneling, but it's not very likely actually. You're more likely to get power and work out how much time you need to use your solar heater for. And then you would use that energy that you're getting in, say 100 joules per second, right? How does that 100 joules per second, what does it do to the temperature of a certain mass of water, right? So it's just going back to topic 3 and using the specific heat capacity questions, formula, sorry. And now you can go back and practice these questions.